So, good morning. First of all, I would like to thank whoever is responsible that I'm here. Thank you very much for that. And I'm an experimentalist, so there will be pictures and real realizations in a lab which is in Heidelberg at the Kirchhoff Institute. And as an experimentalist, if you talk about universal time dynamics, you have to be specific because you're looking for a certain system, and you're looking for physics which is actually general, which doesn't depend on details of the system, because the systems are a very special regime. For example, quantum phase transition is very general, and it doesn't matter if I do this in my ultra-cold temperature or very hot temperatures, if I have the same universality class of the transition. And that's the thing we are after, and we are after doing this in time dynamics. So I decided I wanted to give the talk about two topics we did recently. Well, this is 2015, so some years ago, where we took the system, the ultra-cold gas system we have, we quenched it close to a critical point, quantum phase transition, looked for the dynamics. And this I will skip today, so I will concentrate on the latest results we have, which is in a what we think is called, name it universal time dynamics. Okay, so I skip this point, and if you have questions about this, we can talk about this topic afterwards. So the whole thing, as I said, is done at the Kirchhoff Institute for Physics at the University of Heidelberg, and recently we found synthetic quantum systems as a group of people working on these kind of well-controlled systems we have at hand with these ultra-cold gases together with theory. Okay, so if you are in Heidelberg and you work in the Kirchhoff Institute, you always like to look for connections to Kirchhoff. Kirchhoff, you know, from the law of currents and nodes. And Kirchhoff looks like this, so you can spot him. This is this guy here. This is Bunsen, this is McRoy. And these two people were in Heidelberg at the same time, and they were specifically interdisciplinary because he is a chemist and he is an experimentalist physicist. And he could actually get samples which were purified. Actually, the water around Heidelberg has lots of alkali atoms and also rubidium. So rubidium was found in Heidelberg in 1861, and it was done by Bunsen could extract it from the water and purify it, and Kirchhoff could do this spectral analysis and show that this is actually a new material. And well, there's a long story about rubidium, and the story I'm interested in is 1995. There was a Bose-Einstein condensation of this special alkali atom. It turns out to be the simplest. It has nice properties. All collisional properties are nice. So actually, if you start an experiment, you do this with this kind of species. And that's what it looks like in Heidelberg. So we have the simplest Bose-Einstein condensate you can imagine. The speciality about it is we kind of made it simple as possible, so we can run the experiment 24 hours, 7 days a week. And why is that? We want to do statistics. So we are always going for averages, ensemble averages, and then make statements about the ensemble averages and analyze these. One context was entanglement and detecting that there is entanglement in the system. And today I will show you how we detected with that what we call universal time dynamics. So universal, so actually the experimental system we have at hand allows us to do experiments with these kind of sublevels. So rubidium has this hyperfine structure. And what we can also do is we can manipulate these states. So suppose we condense into this kind of specific magnetic substate. We can put this into optical potentials. You have seen it most likely before. The speciality in our case is that our lattices are large. We have single-site resolution, but we are not interested in single particle physics, but always in the continuum limit. So it was working in the regime where this is about 500 particles, but with a very good spatial resolution of about 1 micrometer. So we're not going to count particles one by one, as it's done in these nice, beautiful experiments and microscopes, quantum microscopes, but we're looking for collective variables. And actually the fluctuation of the collective variables, which then gives you also indication if there is some quantum features in there. So this is an example. You can do this by superposing lattice beams or light beams in this form. You can also use the internal degrees of freedom here, and the first thing we did is we used this kind of two states, which allow you to realize a pseudo spin-and-a-half system with a speciality that you can change the interaction strengths between the two with a Feshbach resonance. And that's what we also might have heard. Feshbach resonance, you can do everything. You can have interaction strengths and diverging. And our rubidium is very simple. But that's why also there is no Feshbach resonance close by and useful. So here you have to use an open channel of Feshbach resonance, which means you can change the interaction between the two species, but they live for a certain time. Actually live very short, so you have to only limit it to short time dynamics. That's what is supposed to be the first part of my talk, is that it can tune everything, you can look for dynamics, go from miscible to immiscible, but you're always stuck with time. So you can only look for short time dynamics, okay? And that's what we are not after. We are going for long time dynamics, and as you will see. So now if you have those two states, and you do this by, what you see here are images, you just take a snapshot of the particle number, so we count the out particles or detected particles by shadow, how many are up here and how many are down here, and this is the two images. So now we can do this also for the manifold f equals 2. There you do it a little bit differently. You take a Stern-Gerlach, so you apply a real magnetic field gradient, and you separate these individual clouds here into these different components, and so we can measure the particle number in each of these components. So that's the only thing we can measure. We can measure particle number in the substates. But we can do this also for the lower manifold. So essentially we can measure all occupation numbers. You name it, we do it. Now occupation numbers are sometimes not the thing you're interested in. You want to see, for example, coherences between those two levels. But there's another thing which comes into play, namely we have full control of linear coupling between these different levels. So we can always rotate the spin one in another direction and measure always in a set projection. So that's the name of the game. What do you have to do before? What unit area do you have to do before you do your measurement in order to extract the interesting variable? And especially in the context of entanglement, this is an issue. And also here I will show you that we have to do a unit area before we detect in order to get the right observable. Okay, so this is the experimental system at hand, and we are going to work with f equals 1 in the following. Okay, so universal. Universal is theory people, most of you are theory. I guess everybody's theory here. Any experimentalists here? Okay, I'm the exception. So universality is extremely interesting because if you found the basic ingredient, you can take very different systems and very different realizations in nature and explain what happens. For example, critical exponents, close to critical points. And here the question is, what can we do in the direction of quantum dynamics? And if you think about being very different, you might choose as different systems as possible to show that there is the same thing happening. And from the experimental point of view, the most extreme difference, I would say, is LLEs at CERN. So this is high energy physics experiments, scales. This is a human being, so this is about 10 meters. And the experiment I showed you we do is in Heidelberg, which is at the same scale looking like this. Okay, so this is about 1 meter. So this is a factor of 10. But this is irrelevant, right? For universality, it doesn't matter what you have to do experimentally in order to see the differences or have a different realization of the system. And it's hard to imagine that here the same thing happens as here. And generally it does not. But specific properties are similar. Okay, so now what happens here is actually you smash heavy ions, lead, for example, in this case, with about 5 tera electron volts on each other. And what an experimentalist does is building a detector around it in order to detect the particles coming out of this collision. So it's a very indirect way of measuring what was there before, but there's no other way. So you smash it, and I will explain this in a little bit more detail in the following. You smash it, you wait, and then you measure what comes out. And what you measure comes out, you have all the tools, you can measure energy, you can measure momentum of all these particles, and from that you can infer or actually check if the theoretical predictions of the development of the system is indeed confirmed experimentally. Now this is under an energy scale of 170 mega electron volts, or if you put it in temperature, it's about 10 to the 12 Kelvin. So it's the hottest thing we can produce on Earth. So now the coldest thing you can produce on Earth is this thing. It's a BEC. It's about 10 nanokelvin, so 20 orders of magnitude different. And there you do a similar thing. You detect particles. In this case, this is an image. I showed you before these blobs. Now this is a continuum. And this is an image where you see this is the m equals 0 component. This is the plus component. It's the minus component. It's a 3-component Bose gas living in the lower manifold f equals 1. And what we can analyze now is actually also particles here. There are about 70,000 particles, which actually not so far away from this thing. It's actually a little less on the left side. But this is what we analyze. So we have here spatial resolution, and we can measure spatial correlation functions and analyze them. So now the difference between those two systems, the system we want to look at, is 20 orders of magnitude different. Okay, so it's the maximum span in temperature you can do on Earth. So the hottest and the coldest. So that can be similar is hard to imagine. So it has to be a specific aspect which can be the same. And the specific aspect is actually depicted here. So this is the whole scenario, and I'm not an expert in all these details going through the system, but essentially what you have is you have this nuclei, they collide. In this case, they collide off-center. You produce a density distribution, energy density distribution, which has a certain length scale, but it's random. And then there's an evolution, which people try to explain theoretically with viscous hydrodynamics. And then actually what you have then is chemical freeze-out. So essentially you get particles out, and later on you have kinetic freeze-out, which are almost about the same time. And then what you get out here in this track, and this is now a different color scale because this is the Rick experiment and the other one's Alice. They have different colors, but they measure the similar thing, so what particles come out. So at the end of the day, you ask what particles do you get with what energy? And you can measure extremely interesting things, like, for example, what is the kind of energy in a certain direction? Is there a kind of radial dependence? And it turns out, yes, there is. Because if this is off-center, you have an ellipse produced. And essentially, what this hydrodynamics tells you that it expands in this direction faster than in this direction. And the faster here you see in real energy. In our case, this you can do with fermions strongly interacting, similar behavior. You measure directly kinetic energy. You measure the particles go faster out if they're stronger confined initially because of the interaction. But you can imagine that detecting here, getting something about the very early time dynamic is very hard. Because you have all the things in between. Even this is not clear how this emerges and why this is directly the case. So there's no direct connection from here to here on the theory side. So where is the thing we can enter? And obviously here not, because here you have all the beauty of QCD. But here at the very beginning, it's actually only gluons which play a role. So it's the gauge fields. And we have also bosons. So this already points in a similar direction. As well as we have 3 components, not as many as they have here, with n large. But at least we can hope that we can see similar thing. So the idea is, can we see this initial dynamics which starts after this kind of initial energy distribution distributing itself, and then actually becomes this description via viscous hydrodynamics. And there was a theory behind it, and there was a scenario predicted or suggested, which happens there. And the scenario is the following. So this is actually what Jürgen Berges explained me. He's in Heidelberg, and we started working on this thing, and so he explained this narrative I can give you here, because I cannot do any theory myself. I can just repeat what people tell me, and certain things resonate, others don't, and so I tell you what resonated with me. Okay, so the scenario is the following. So this initial condition is far from equilibrium. It's definitely not in equilibrium and not close by, and you just go a little bit away from the equilibrium, and you will relax back. It's far from equilibrium because you smash the thing with high energies, but you can put this in another footing. You can ask, well, what is this kind of distribution, energy distribution? At what length scale does this happen? And what's the occupation number of this length scale? And so there you are in this regime where you have actually weakly interacting particles, but you have strong occupation numbers. So one thing to be extreme means you have a certain length scale and you put there a high occupation number. So even the system is now weakly interacting, as in our case, bosons are weakly interacting, the occupation number is large, and what matters is the product of the two. So you get a strongly correlated system as it evolves. Okay? So the narrative is we have this initial condition which is far away from equilibrium, and it develops very quickly away from the initial state. So somehow it forgets very quickly where it comes from. And forgetting is actually also an ingredient for this renormalization group idea, that if you make scales larger, the system forgets about details, and only the relevant things survive in the limit to be large. Now here this is all in time, so the thing is you develop here quickly, ideally with an instability exponentially fast, and that we can generate in our gases too. You develop into a regime which is described by dynamics which is self-similar, and I will explain this in a minute. And this can be only a transient phenomenon because you are in a closed system, there is no input and output of energy, so essentially the system will then later on go away from this universal behavior in time and then maybe relax to equilibrium or get stuck somewhere. Okay? So we cannot say anything about this in our experiment, but we can say, or at least I will try to convince you that what we see is consistent, that we get close to something which you can associate with a non-thermal fixed point, which is synonymous for seeing scaling in time. So what means scaling in time? So specifically, we are just asking now about the early dynamics of this behavior, and this is experimentally hard to detect here, but both guys can do this. So universality means what? What do I have to do as an experimentalist? Well, I should find a certain observable f. actually they take certain correlation function, a certain degree of freedom, and look for the structure factor, i.e. the Fourier transform of the structure factor. And the prediction is that you get a functional form for a certain time t, which changes in time in the following manner, namely it gets shifted to lower k, so the system structure gets larger, and also the amplitude goes up. So there should be a scaling in time as you go for longer times. You can rescale this distribution to fall on this one here because it's the same universal function, like shown here. And you find beta and alpha, the coefficients. So if you are in this regime, then this should be possible. So we do it differently. If we measure this kind of thing, we show there is scaling, then we claim that we have some smoking gun from this non-summer fixed point there. So at the end of the day, the question is, can you find a universal scaling function, which is specific to your system, but this is a function. If you found it, then you only have, what you can do is connect different times by rescaling the case with a certain scaling exponent, and also the amplitude is modified by another scaling exponent alpha. Now the behavior here, what you see here is just transport in k space. So essentially you have redistribution in k of these special excitations, which are such that it's self-similar. And this must be very specific. It cannot be like simple, just like local k scattering. Essentially, in order to understand that, what you need is a k-dependent scattering or cross-section, or in the Boltzmann equation, something where two particles come together. It depends on the momentum, how they redistribute the momentum. Okay, so this is very specific that this happens, and it has been shown for this kind of model systems for this initial phase of the quark-gluon plasma or heavy ion collision, that essentially what you see there is exactly this behavior, numerically and as well as theoretically in a certain limit, namely in ON symmetric models with n going to infinity. That's what the people tell me. So n equals 3 is not infinite. So the question is, does it survive in n equals 3 or not? So because you have a 3-component Bose gas. Okay, so this is the thing we are after. Can we see time dynamics transient and show that this is rescales in time in the following manner? Another issue is that alpha and beta are not independent, because here the transport is described by transport of conserved quantities. That means whatever goes from here somewhere here, it is not lost, it's just redistributed. That means alpha is connected to beta because the integral has to be constant, and the integral of being constant is the conserved quantity. Okay? So essentially, you would like to find the observable such that alpha is about approximately beta, or the same, then you have found the conserved quantity which is transported in this very, very special manner. Okay, so this is the thing we try to find in Bose gases. And ingredients we need here is initial conditions far from equilibrium, instabilities, and then possibilities of detecting observables and the structure factor as a function of time. Okay, so what do we have at hand? Since the talk was still this morning planned to have 2 parts, this was the first part, so we detect this pseudo-spin half system. But this has limitations because you have to tune to make it interesting, to tune the interaction between the two systems to get kind of a miscible-immiscible transition. And there you have to use a Feshbach resonance. So there you're always limited in time. You cannot go for a long time because the system just decays because of collisions and forming molecules. So for the thing I would like to talk now is we take the lower manifold, but take the situation that you have particles distributed over those 3 levels. These are the magnetic sublevels of this hyperfine state. So we have a spin 1 system at hand, and we can prepare very precisely initial states. And then we have control. What kind of control do we have? Well, the first thing is a single particle control, namely linear coupling. We can couple these levels with a certain frequency omega, which turns out to be a spin rotation in spin 1. So we have arbitrary spin rotations available in the experiment with very high precision. Why is that? Because we were interested long time ago, or 2 years ago, about entanglement, and there actually you'll measure fluctuations after rotations. And so if the rotations are random and have some noise, then you will always spoil a quantum noise. So this we know very well, and we can do this on the quantum limit, i.e. we rotated it and then we get a coherent state. Now the other thing is the interaction, and this is specific here. These interactions of 2 zeros has to conserve delta MF equals 0. So essentially they collide like this, but they can also collide like changing their spin. So we have coupling between those 2 levels, or those 3 levels via interaction, which is two particles here collide and produce one particle here and one particle there. So you have these pairs produced, spin up and spin down, and this is one process which leads to certain dynamics in the spin degree of freedom. And then there's an additional thing we have under control, which is the relative level shifts between these levels. And here I already took out the linear Zeeman effect, which is shown here, and left the quadratic one. And they are also, if you just take magnetic fields, you're limited in kind of moving these levels because they always move up the same way. But here we can control the middle level with a microwave dressing field. Where you can just shift this energy level up and down. This is our control parameter, and we can tune it as we like. Okay, so this is the system we have at hand, and now we can ask what to do with it. And the first thing we do is we take an extended system. So this is 80 micrometer. This is a Bose gas picture of it, like a shadow. The resolution is 1 micrometer, so we can resolve very well what's happening within this cloud. And this is about 60,000 atoms. This is realized in a trap, dipole trap. And this we can now start to analyze. Now this is just a density, and you don't see the spin degree of freedom, right? I mean, this is just like how many particles are there, but you're interested in the spin degree of freedom. And the spin degree of freedom is interesting because there's a phase diagram for the spin part. And the axis here, this is Q, this is this level shift I told you we have under full control, so we can, this axis we can change. And the C1 is actually a very specific parameter which gives you the coupling strength between this collision going and spin up and spin down. This is atom specific, and it depends on your manifold you're using. If you take F equals 2, you are up here, you have a polar phase, i.e. in this the ground state, that's the mean field ground state, is just a 0. That means if Q is negative, or positive in this case, it means like this is just the lowest state. Everything is in here, that's the ground state. The same thing is true for this C1 value, which is actually for F equals 1, where we are working in. So here there's a phase, if Q is large, like largely tuned, then it's clear this is the ground state. But here it's very interesting, as you change Q and make this energy difference smaller and smaller, there is a quantum phase transition where this spin, which has no expectation value, gets an expectation value in the easy plane. So essentially you build up from nothing, you go over the transition, you build up transverse spin and in any direction. Okay? And then if you go further, then this goes to easy axis ferromagnetic phase as you change Q. But we are going to do the experiment here in this phase. So easy plane ferromagnet, the system in the ground state would have a spin in the XY plane, XY plane. Oh. Good. So now the question is how do we detect it? Because all we can measure is particle numbers. Okay, so now for this state here, you would say, well, this is, I can detect this. This is the MF equals 0 state, and we can measure that. But we are actually interested in, if I plot this in a Bloch sphere with Fx, Fy, and Fz defined as here. So Fz is always particle number difference between spin up and spin down, or plus and minus 1. And Fx and Fy are actually coherences, sum of the coherences between the two states, this state and this state, the sum and the difference of that. This is the equivalent of Fx and Fy. Okay? And remember, we are always dealing with collective variables. They are always in our imaging model, like volume, they're always n particles. Okay, so we can always measure locally expectation value of Fx, Fy, and Fz. Okay, so now if we have this situation, it's the ground state, we are now in the phase diagram here, we want to get to here, how do we do it? Well, we apply a microwave field. Actually, it should be farther tuned to another level. And with that, we can tune this level up and down. This is called dressing, a well-developed technique. You just shine in, the more power you have, the higher this level goes up. So now we can tune it, and tune it such that the Q is now here. Okay? Now what happens here microscopically is this level shifts up, and then the spin-changing collisions can start to happen, and they build up in the ground state a certain structure, namely they build up that you have a transverse spin, F perp, building up, no Fz projection, but the phase is random. Okay, you don't know where this spin points to. It's a random phase. Okay, so now if you detect this, then we would see, and this nothing. It would be the same, even if I have this, the Fz projection is 0, and that's what I measure with occupation numbers here. They are 0, so it's 0. But I would like to see if there is some spin in this plane. And how do you do this? Well, you just rotate the whole system. You rotate this spin out of plane, and then suddenly all what you got in x and x and y, you get in fz and fy. Okay, so we measure now the z projection by directly detecting occupation numbers here and here, and that we can analyze as a function of space. Okay, and then do spatial correlation functions. So we have to do this kind of trick, but this, again, as explained, this we have under very good control. Okay, so now this is what it looks like in an experiment. So this is the state we can produce, and that we can do very well with very high purity. This state is easy to prepare, all in MF equals 0. You take an image, and the image you see here is done actually, you take the cloud, you take a Stern-Gerlach, and then image. So if you take a Stern-Gerlach and you just get one cloud, that means you're an eigenstate of one of these MF states, and in this specific case, it's MF equals 0. So now if we rotate this, okay, there's no expectation value of this spin vector, yeah, but it has fluctuations. Okay, they're there, so, but in fluctuations you can see in the experiment. So if we rotate this, then actually this ellipse turns up into fz, fy plane, and then we measure again fz. What it looks like here in this occupation number is all we do is with this rotation, you put everything in the side modes here and measure these side modes. And that's what it looks like. Same thing, just rotate it first, and then take an image after the Stern-Gerlach, and you get everything in the plus mode and the minus mode. But now before it was 0, and 0 minus 0 is 0, here there are occupation numbers, and occupation numbers minus occupation number is non-zero. It's fluctuating. It's exactly these kind of fluctuations you see here are now showing up as fluctuation in particle number differences. So we see these quantum fluctuations of this spin, and we can analyze that. So now all we do is we take fx as a function of y as a position in the cloud, and you see fxy is actually fluctuating. The differences here are not constant, they're fluctuating, but this is exactly what it should be because you have this uncertainty anyway there, which is the quantum noise. Okay, so now we have access to fx as a function of y, and we are in the easy plane ferromagnetic phase, so we can actually measure projection in x direction as a function of y. Okay, so now what's the hope? Remember, the hope was that we see some universal in time. So we can do the experiment. We start the experiment here. We quench it to this easy plane ferromagnet, and then see what happens. And we take a snapshot, we prepare it again, we take a snapshot, we prepare it again, take a snapshot. Each of the snapshots takes about 40 seconds, and this happens 24 hours, 7 days a week. So these are examples you get out. Okay, so as you go along with time, you see suddenly that this, and this is this fx projection, actually fz, but this is connected to fx projection, and you see for short times you build up strong fluctuations in this spin. So essentially, you're on top of this inverted parabola of this free energy, and you start to explore the space, you run down with an instability. So this is unstable in respect to this initial state, and this is all well explained in the Bogolubov theory for short times, and you would expect certain modes build up with certain length scale, because they're most unstable. That's what you see here. But this is actually not what we're after, because this instability is, remember, this was the early phase of this triangular, the trinity graph. It was the initial state, and you forget exponentially fast. So essentially here you don't expect scaling, you just forget. And now it turns out in this case down to here, in this regime, we see the scaling, and then later on we lose it again. Okay, and I will show you how we see that. Okay, so this is repeating what I said. So essentially we have this initial dynamics, which is exponentially fast, instabilities, which is happening here. Then there is some universal time dynamics, which happens between 4 and 9 seconds, where you already see it's a factor of 2. So if you don't know there should some universality there and some scaling, a factor of 2 in experiment showing exponents is hard. But if you have the theory background, then you can try to see this. But you also have to analyze this data not by just looking at one realization. You have to look at the structure factor of these experiments. So you have to repeat the experiment over and over again. It's random from shot to shot. Then you do spin correlation function. I will show you what correlation function we have to do. And then do the Fourier transform of that, and that gives us the structure factor. And then the hope is that we get this scaling behavior. Okay, And I have to say, at this point, there was no theory prediction that this works in this system. The first prediction was, in 1D, nothing happens. It's special and nothing can happen. And then we did the experiment and it happened something, and then they found out actually there can something happen because we have to spin 1 degree of freedom, which helps. Okay, so this is a 6.5 second realization. This is fx, and you see this is like this. But if you understand this, and it took us also a while to understand what we have to measure, it turns out we don't have to measure fx. The observable we are interested in is the angle theta. So we want to know how is the angle correlation in this figure, in this realization. So how is the spin is in the plane, and I'm asking how is the angle correlation in as a function of y of this direction. So now obviously this is not what we measure here. So the main problem is that we don't know the length of this vector. If you would know the length, then also the projection, if we know the length, then the projection would be good enough. If the phase does not wind up many times. And it turns out it does not. It's always below 2 pi for the experimental settings we have, which we found out later by doing other experiments. Okay, so how do I get theta out? Well, one thing we can do is, suppose we take many of these realizations and we measure just the spin, fx, averaged over all realizations. Okay, so I just ask what kind of fx's do I get, and if I'm living on a circle, then I would expect a distribution of probability to have fx of this form, namely it's peaked at f, the maximum fx you can have. This is a width to it because it's quantum, and so that's something we would expect. But this we can do. We can just do many experiments, and we average over all experiments. We ask about the statistics of the spin, of fx spin, and what we get out is this. So this is for 6.5 seconds, many realizations, and then you do the statistics, and you see they get this double-peaked structure, and from that you can infer that this actually, this maximum here corresponds to the f burp maximum. Okay, so we have something living on the circle. This is indirect. We do now new measurements where we show indeed we have this kind of behavior, but this is the first result and published on the archive in this manuscript here, and that's what I'm telling you. Okay, so now we know what f burp is, the length of it, and we can do this as a function of time. Okay, and that's what it is. So this is not only we measure variances, we measure the full distribution of this spin. So you start with this very well-defined spin initially, then it spreads out over time. This is actually all not scaling yet. But then here, this regime, it starts to do scaling, as you will see. And you see the double-peak structure survives. And then actually for long times, after 9 seconds, 11 seconds, it goes away and gets Gaussian again. This sounds like wonderful. You run to this very special point and go back to the Gaussian state. But actually, we don't know from here, from 9 seconds up to here, what's really happening there. It might well be that there's heating in our system, and actually heating spoils this behavior. But for a time up to 9 seconds, we can do the analysis and find what was kind of predicted. Okay, so this is actually an interesting aspect that you can measure the full distribution functions and make something out of that. We start analyzing this if there's a second moment and a fourth moment, how does it develop in time, and there's some structure in there, but we don't understand it. So it's just like from you, that's something you can do, you can measure and compare with theory. Okay, so we can, from these points here, we can always extract f burp. Here we cannot, and here we can also not. And this we need because we want to have the angle. So now if we have this f burp in situations where we can really read off, we can deduce theta just by doing the arcsine of this function of fx, which we measured, f burp we extracted, and then to do the correlation of f theta y prime, and to the Fourier transform of that, and that's what's called structure factor. Okay, now f theta of k we can now analyze as a function of time, because for each time we do this experiment over and over and get an ensemble average, this f theta of k. And that's what it looks like. So here is the momentum, so this is the spatial degree of freedom, 1 over the Fourier transform, and this one is the structure factor. And you see we have 3 orders of magnitude in dynamical range here, and you see that the structure factor drops off in a peculiar manner. It's a double log plot, so here you see something like a power law. And here you see some function which you can fit. And what we chose was this kind of distribution. So if psi would be 2, then it would be a Lorentzian, i.e. exponential decay of the correlation function. So we fit this here and we get this kind of agreement. It does not fit for all k, so for high momentas this deviates, and it's also expected that this kind of behavior I showed you, this universal dynamics, is only for the infrared physics. Okay, there's also something happening here in the UV, but it's different. kind of wave turbulence kind of phenomenon. But we are interested in the infrared, so actually flowing of k towards lower k, high k to low k. So different to the vortices, which decay into smaller and smaller vortices, it's here the theta fluctuations get larger and larger and larger in distance over time. Okay, so this is actually good. We have a function, we can fit it, and now we can use the theta as a function of time. Because what we are asking is there a regime where one function explains the structure factor? Okay, so we do this, and we find the following. So here is time from 0 to 12 seconds, and we extract the theta exponent from our experiment, and you see at the beginning you have 4, you have some distribution, you fit this function to, but then at about 4 seconds, it settles down to one value. So essentially what you measure here is the power law decay here in this regime, and it turns out to be 2.6. That's a number which might be, has some universality aspect, but we have no prediction for 2.6. Okay, that's what we find. And you would say, that's cool, because it's the first indication we need for universal time dynamics, namely a scaling function. So we have a function, and now we ask, does the function really kind of rescale in time? Okay, so the first thing you can do is, if you have this behavior, you take the simplest case, take one number, namely the k equals 0. So we take how the whole system develops, actually I should do it like this, how the whole system develops in theta, okay, in time. Okay, so we do this as k equals 0, we can extract this experimentally for our system, it's a system size, and that should go with t to the power alpha, okay, and that's what you get. So at the beginning you get something, this is k equals 0, then there's some behavior, and then you get something. Now there's a green line in there, and the green line is not coming from putting this into data, but coming from the further analysis we did, but this is a power law, okay? Power law with a certain exponent is about 0.3. But you would not say this is a power law here. It's just a one number, and you ask how the one number depends on time, okay? But we have more. We have the full functional dependence, okay? So these are the structure factors for the different times, for 4 to 9 seconds. And now we can ask those distribution functions, the full function, rescale, not only one number. Okay? And so we do this, and we would expect actually we get a beta out and an alpha out in order to get this on a universal curve, and that's what we get. That's what it looks like. So now these data are rescaled, and what you see is they fall on this universal curve with this one exponent 2.6, and out of that we get alpha and beta with a certain error bar. Okay? And what we find is alpha is 0.3 and beta is 0.45, okay, or 54. Okay, so this is a half approximately, and this is a third. Okay, now this third we were extremely happy about, because the first experiment we have done, and this we took actually for a year, we looked at fx, so just a projection, and the projection actually had alpha equals 0. And he could put it up and down, say error bars, and like its alpha is very hard to distinguish experimentally and measure it, but it always was 0. And actually it turned out we looked at the wrong variable. We had to look at theta in order to see this. Because the whole process here is described by transport of conserved quantities, and we had to look at the conserved quantity. Because in this case here, what happens due to, and we think now it's heating, the length of the spin vector decays in time. But the theta correlations, they behave like what you see here. Okay, so if this is true, then actually taking this result, or taking these functions and take the integral of it, we should find that it's approximately conserved, because alpha is not so far away from half. It should be exactly 1/2. It should be t times t is dimension times beta if it's conserved. So it should be 1/2, but it's not. And so we can do the integral and see what the integral does. So we take the integral of the structure factor as a function of time, and you see at the beginning you have something, and then I don't know why this jump happens exactly at 4, but this is what it is. And then it's constant, more or less. It's decaying slowly, and that is also consistent that alpha is not equal to beta, but there's another decay mechanism in there where we just lose spin or theta excitations. And then after about 10 seconds, it drops down again. Okay, so this is also indicative for what was suggested, that we have transport of conserved quantities in the regime where you have scaling. Okay, so this is an important issue, and took us a while to get experimentally. So now out of that, these parameters are consistent. Alpha is not 0.5 because we still have this residual decay, but it's a sort of quantity which emerges in the system, it seems, and is transported in the way which was self-similar, is self-similar to our position. Okay, so now remember we had this kind of case that, okay, this happens now for one specific initial state. Okay, I said I start with polar state, i.e. everything is 0, let it evolve, have instabilities, and things evolve. But it should be, if this is true, it should be a robust phenomenon. It's not fine-tuned that it's for one specific case you get this behavior. It should be also for different initial conditions which fulfill this extreme condition. We should get a similar behavior. Okay, and that's now a strength of our system. We're not relying on heavy ion collision, and what you get out is what you get out. We have our system under control. We can write in structure in a spin degree of freedom externally, and then look what happens. And so there are different realizations of this spin degree of freedom. And here you see the Fourier transform of the transversal spin. And so you see they're very different. One is peaked, one has almost the same structure as you get for a long time, and one is just like flat. Okay, and now you can ask, do they develop in the same way? And it turns out, well, you have to wait. You have to wait about 4 seconds. And after 4 seconds, you get this behavior, namely these curves fall on top of each other, scaled with the same exponents, with all the error bars. But all these different initial conditions have the same exponents, 0.5 and 0.3, plus minus the error bars you see here. So this is actually confirming different aspects. One was, do we get a scaling function, and does the scaling function depend on time as expected? Namely, by rescaling of time, you get a collapse at amplitude. The initial conditions, a robustness is shown here. So essentially, all initial conditions you did, which were very different, lead to the same. And unfortunately, we cannot say something about this line, which would be extremely interesting, that it deviates and goes down, goes maybe close to equilibrium or not. And this is actually for future work, definitely a route we want to go. And for that, we had to find out what are the mechanisms that we lose our spin length, and that actually turns out to be temperature, which is a small heating rate of about 2 nanokelvin per second. It's not large, but it over 10 seconds, it builds up. Okay, so that is actually the thing I wanted to tell you about this universal time dynamics. What we have at the moment, there's many things to ask. We can also go for not 2-point correlation functions, but 4-point correlation functions. And then also get a handle on, can we measure that these kind of scattering processes have a momentum dependence? That's all out there, and there's lots of things to do. But there's even more, and this is actually not here. This is in Cape Verde. And these atomic systems we have at hand, and we developed and we kind of perfectionized in control, allow you to do very different things too. For example, what we have done recently is we dated water in the ocean. And we know in front of Cape Verde, the water is about 800 years old in 4,000 meter steps. Maybe you're not interested in that, but I find it extremely interesting because we use the techniques for both gases, the cooling techniques, and perfectionize this for detecting argon-39 atoms, which are extremely rare, 10 to the minus 15 to 1. And with that, we can do dating. So this is one project we have. Another thing I didn't talk about is actually our old business for many years is entanglement production in these both gases, and this 1 degree of freedom turns out to be very robust. And you can actually distribute entanglement by first entangling the system locally with a spin degree of freedom, just let it expand. And what you get there is you get a non-local entanglement, Angel-Podolsky-Rosen correlations in a Bose gas. There's also connected work in the Klemp group and Treutlen group. And all these 3 works are published back-to-back in Science in April. And the thing I told you today was about universal time dynamics, a very specific aspect of it, namely for the spin 1 system. Jörg Schmidtmeyer has recently also a result on the archive where he actually looked at a single component system, and there actually the dynamics can boil down to really solitons in the gas, which is different to what we have here. Here the whole picture is a wave picture and scattering of waves, these theta waves, and the solitons is a different issue, but maybe it's another side to what universal dynamics is about. And with that, I thank you for your attention.
Questions?
Somewhere that you're crossed in, or and in 1D you're quenching, so you always have finite temperature. So what?
Yeah. This is far from equilibrium. There's no ground state properties here. I started with ground state properties in order that you get a feeling what the Hamiltonian structure is. But what you do is really hit hard. And then you ask what happens. And that it has to happen like this is for me not clear. But experimentally you can do it and look for this structure. And if you find it, there is something below it. There is something which describes your dynamics in a simpler way. And the simpler way is I give you the conserved quantities, and now you can build a theory which shows you that this conserved quantity is transported in this way. Okay? So you're asking why should it happen, right?
Why should you have such a strange exponent?
Well, strange is one has to say yes. So the ON models they studied in detail, and they find out this beta is a half. And there, alpha is d times beta. Okay, d is a dimension. So there you do, like theory can do 5-dimensional things too. I'm a little bit stuck with my 1D. And my 1D is also not perfectly 1D, it's also quasi 1D, which is one aspect, which actually explains why the exponent theta is not what it should be a half, but another value. But it turns out that this behavior here, if you do this with the spin 1 system for these very specific interactions, you quench it in pure 1D, theoretically, homogeneous. You also get dynamics in this way, namely rescaling in time, but then the exponent beta is a quarter. And why it's a quarter, I don't know. But there is something behind it that it seems like the narrative is like the system forgets. And so this renormalization group aspects might be applicable. I'm repeating, I don't do this myself. And then you flow to something which is a fixed point. And the fixed point is scaling. But now it's in time. It's not like the phase transition picture. It's another thing. It's an object which tells you that the wave function, these correlation functions have a certain structure, namely rescaling in time and space. It's something different. Yes. It's 1D plus, if you take kinetic dimensions, if you like this picture, this is 1 plus a letter. It's a letter. It's not 1D, you have a spin degree of freedom, and so you can see it as, so a system is not one-dimensional, it's three-dimensional, one-dimensional, 3 times one-dimensional system with a very peculiar manner of coupling. So it's not 1D, it's not single component. So maybe that's one way out of this kind of dilemma. On the other hand, it's really like here, it's a dynamical system and showing this structure. And now actually the name of the game is this structure always a half? No, we have an example where it's not. Other universality classes too, which is, that's actually what Jürgen Berger tells me. This is his dream. That you can look at time dynamics and also classify it for certain phases, namely extreme conditions. You can classify it via exponents and scaling functions. Doesn't have to be, but it's indicative that all ON models, n independent, and now we have n equals 3 approximately, show the same. I find it extremely interesting because it's a very different route. Yeah? You have these integrable systems which get stuck. You have this many-body localization, which also got stuck in a certain manner. And this is also a transient which happens, and it happens not always. You have to be in a situation where you have high occupation numbers, that the product of interaction and occupation numbers is large. That this is the ingredient you need. At least that's what I'm told. So it's not general, but for the specific things, for these very extreme conditions, you hope that you see this in very different systems. And Jörg Schmidtmeyer saw it for solitons. Maybe very different, but...
Any more questions?
People in heavy ion collisions, do they see any, can they do experiment like this?
No, for them it's very hard because the readout is after the chemical freeze out and you are interested in a very early phase. And so for them it's very hard to see this in time. I mean, they have no time resolution. Now that is one idea they told me is like you have these very early photons coming out. Maybe they have some information about this early phase, but I don't know more about this. So here, actually, the narrative here is that this system allows you to look at the short time dynamics. It does not have the beauty of QCD and also not this kind of hydrogenization aspect, but it has the initial part which might be captured here too. And this is actually the first experimental demonstration of this phenomenon. So this is actually, you see, I hope that there are more people showing the thing that this happens. And then maybe it's another way of understanding dynamics in very special situations, I have to repeat, which have a universality.
Do you know other systems where you can observe this kind of behavior in non-thermal fixed points?
Yeah, so the non-thermal fixed point for me is synonymous for seeing the scaling I explained, okay? So it's because the scaling, as a fixed point, I have my problems because it's a theoretical concept. This thing here it's kind of defined what I have to do. And what has been seen recently is in Jörg Schmidtmeyer's group, they did a one-dimensional system and a temperature quench, and then asked about density fluctuations. Actually, they looked at momentum distributions, and they also found that there is a distribution which changes in time with exponents of 0.1. Alpha and beta is very, very small. But they also see that there are solitons in there. And this is something what also Thomas Casenza looked at numerically, that if you have this vortex in 2D, and you produce this very extreme situation that you have vortex up and vortex down, periodically arranged, so the total angular momentum is 0, what happens in time of the system, and you see also that there you develop currents in a very peculiar manner, which are self-similar changing, like you see here. The thing I'm showing here is from a theoretical point of view different, because there are no topological excitations in our system. So the question is a little bit, you have both. Typically you have both. In this case, it seems you have only waves. In Jörg Schmidtmeyer's experiment, you have only solitonic excitations, and very often you have a mixture of both. But they behave differently. And you ask, are there other systems? Well, I would now say this should be very general. It's like whenever you do a quench, but you have to do it specifically. You have to start with a system which has a characteristic length scale, and you have to put all your particles in this length scale, which is typically not done. It's a very specific initial condition called extreme. So occupation numbers are large, and product with scattering is large, and then this should happen.
Any more questions? If not, let's thank Markus again. And we have a coffee break now, and we'll be back at 10:50.